All right. So at this point, we've knocked out pretty much everything in chapters 4, 5, and 6. And if you note from the syllabus, chapters 4, 5, and 6, that's the topics that are on exam 2. So it looks like, even though exam 1 is due tonight, exam 2 is going to happen sometime next week. Probably just so I don't overload you with too many exams in too short of a time. I'll check the date on that before I make anything official. But it'll be sometime next week. We'll have the exam for exam 2. That'll cover chapters 4, 5, and 6. All of those are Newton's law problems of one variety or the other. And the big kind of twist to each chapter is that you learn how to deal with different things. In chapter 4, we mostly just introduce Newton's laws. In chapter 5, we throw in an additional couple of forces, like the drag force or the force of friction, that have some special rules that you have to be able to keep track of in order to make use of them. So that's what we do in chapter 5. And then the big revelation in chapter 6 is when we're talking about circular motion, we know something special about the acceleration of the object. And so that's the v squared over r thing. But at the end of the day, it's all still just Newton's laws. We'll be doing a Kepler's law lab on Friday. So normally I spend some class time doing Kepler's laws, but we'll do that on Friday, and that'll work out fine. In the meantime, what we've got today is we're going to change gears in a pretty big way. And the reason that we're going to change those gears is because there are certain problems that if you just try to attack them using Newton's laws and Newton's laws alone, they just become too difficult and it gets too complicated too quickly. And so for some of the more complex situations, you have to attack them in just the right way in order to make sense of them. Let me give you an example of what I mean. All right, let's start with a problem that I know for a fact that we could solve. And then I'll tweak one part of that problem and turn it into a problem that is literally impossible for us to solve. And then in chapter 7, we'll learn how to solve that problem. And not only will we make that impossible problem stop being impossible, we'll actually make it easy. It'll be one of the easiest problems we've ever done. So here's the scenario. Let's start with the problem that I know we could do. This is a problem I could put on your next exam because you know enough physics to solve this problem. So here's a box on a ramp. I love boxes on ramps. Now, what I'm going to do is I'm going to take this box, put it on a ramp, and I'm going to have this guy be, let's say, 10 meters high. Now, I'm going to put it on a ramp, and let's have that ramp make a 30-degree angle with the horizontal. And I'm going to start the box up here at rest, and I'm going to allow it to slide down the ramp frictionlessly. And when it gets to the bottom, what I would like to know is how fast is this box going to be traveling, right? That's the problem we're going to start with, and we know enough information to solve this problem. Let's just do it, right? If nothing else, it's a review for chapters 4 and 5. So to solve this problem, the first thing I'm going to do is I'm going to treat it like a Newton's law problem, because what I know is that this box is going to accelerate down the ramp. How much acceleration will it have? Newton's laws will tell me. The first thing I'll do is I'll identify the forces. What are the forces? Well, there's a normal force from the ramp that is perpendicular to the ramp. And there's also the force of gravity pulling it straight downward. That's easy enough. Nobody else is pushing it. There's no friction to worry about. So those are the only two forces that we're going to have. So when we do these box on a ramp type problems, there's a trick, right? First, we do the free body diagram, but then we move on to our second step where we're choosing a coordinate system and we're breaking our forces down into that coordinate system. The trick for these box on a ramp problems is to not use X horizontal and Y vertical. That's a bad coordinate system to pick, but instead to slant my coordinate system so that the x-axis runs along the ramp and the y-axis runs perpendicular to the ramp. And by doing that, we're going to make our lives a little easier. So here I'm going to say that the positive x direction is going to run down the ramp. And I'm going to say that the positive y direction runs perpendicular to the ramp. Now, when I make that choice for my coordinate system and I break these two forces into their components, the normal force is pretty easy because it's purely going to be in the y direction. It's not along the ramp at all. So it'll be 0 for I hat, that's the x component, plus whatever the normal force is in the j hat direction. Hopefully you guys are getting pretty hip to this. Meanwhile, what about the weight? What about this force of gravity? Call that W for weight. And what's going to happen is because my coordinate system is not lined up perfectly with this weight arrow, I'm going to have a y component into the ramp, and I'm going to have an x component parallel to the ramp. So that's going to make me a little triangle. And what I have to realize is that whatever angle my ramp makes is going to be the same as this angle up here at the top. Once I do that, I've got a right triangle where MG is the hypotenuse of that right triangle. The x component is the opposite side of the triangle, and the y component is the adjacent side of the triangle. And so from SOHCAHTOA, I can break that down, and we've done this a few times. We know the x component is going to be mg, the total, times the sine of theta, where theta is 30, I hat. It's down the ramp, so I'm going to make that positive. But the y component is into the ramp, so it's negative, and then it'll be mg cosine theta j hat. So again, we've done this sort of trick a few times, so hopefully this is not new to you guys. Once we've broken it into components, now the next trick is to use Newton's second law, which is that the sum of the forces equals ma, to generate some equations, one for the x direction, one for the y direction. That's going to give us two equations. In the x direction, I have 0 plus mg sine theta. Those are the I hat portions of my force. So mg sine of, in this case, 30 degrees, is going to equal the mass of the box times the acceleration of the box in the x direction. That's my first equation. My second equation, which we're going to end up not even needing, is that in the y direction, I have the normal force minus mg cosine of 30. So the normal force minus mg cosine of 30. That's going to equal the mass of the box times the acceleration in the y direction. Now, once I get to this portion of the problem, I always pause for a moment and I ask myself, do I know anything at all about the acceleration of the object in this problem? And the answer is yeah, I do. What I know is that this object is not going to accelerate in the y direction at all. If it moves, it's going to slide down the ramp. But that's the x direction. It won't be moving this way. That's crazy. So I can assume the y component must be 0. However, the x component will not necessarily be 0, and I'll have to solve for that. Turns out, though, that's easy to do. Because look, the mass of the object appears conveniently on both sides, which means it cancels, and aha, I know this object's going to accelerate with an acceleration of g, that's 9.8, times the sine of 30, which is 1/2. So already I know that the acceleration of my box is going to be 4.9 meters per second squared. And it's the only acceleration there is, so I'm going to even drop the x subscript. Since I don't have a y component to worry about, this is the only acceleration there is. So that's a Newton's law problem, but it hasn't answered the question of how fast the box will be going at the end. To get that, we're going to have to continue this into a chapter 2 problem. It's a one-dimensional kinematics question because we know the acceleration, we know where it starts, we know where it finishes, and we're looking for the final velocity. So here's my x-axis. I'm going to choose to call x equals 0 the location where the box begins. And so when I do my little one-dimensional kinematics 6-item inventory, and I track which things I know, well, I can always assume the box starts at 0. I know that it started at rest, so that's going to be 0. I'm looking for the final velocity, so that's what I need. The acceleration we've already solved for, it's 4.9. The time it takes to get to the bottom of the ramp, I have no clue. And x final, well, I don't know it, but I can figure it out. Because what I can look at is I know that from here to here is 10 meters, and this forms a right triangle. And I know then that the sine of 30 degrees ought to equal the opposite side of the triangle, which is 10 meters, divided by the hypotenuse, but the hypotenuse is whatever x final is. So if I solve this for x, I have x sine 30 is equal to 10, and therefore x is equal to 10 divided by the sine of 30. Since the sine of 30 is 1/2, that means that x final is 20 meters, which makes sense. The hypotenuse ought to be the longest side of the triangle, so we knew it had to be bigger than 10. So at that point, we've got a one-dimensional inventory, and we know everything in it except for the final velocity and the time. And what are we looking for? We're looking for the final velocity. So I need to avoid any equations of motion that have the time in it. That suggests that I'll be using this equation of motion. And of course, we're solving for v final. V initial is 0. That makes that simple. So I'm going to have 2 times 4.9 times x final, which is 20, x initial, which is 0. And that's v squared. So v will equal the square root of 2 times 4.9 times 20. So 2 times 4.9 is 9.8, times 10 is 98. The square root of 98 is about 9.9 meters per second. Piece of cake. So, what's going to happen it's 9.89, but yeah. So what's going to happen is we could solve that problem without, let's keep 3 sig figs, without too much trouble. We had to use stuff from 2 different chapters to solve it. We had to do the Newton's law problem to find the acceleration. Then once we knew the acceleration, we had to do kinematics. But we eventually got our answer after all of this work. However, if I tweak one thing about this problem, I can make it go from being a problem that's totally doable to a problem that's impossible, at least using our present techniques. Here's what I mean. What if I change the shape of the ramp? What if instead of it being a straight line ramp, what if instead I put my box 10 meters high and I allow it to slide kind of like, one of those like fun water slides at the water park. It's like one of those. So it's going to slide frictionlessly over this weird bumpy shape. And I still want to know the same answer. When it gets down to the bottom, how fast is it going to be going? Now, using Newton's laws to solve this problem isn't going to work for us. And the reason it's not going to work for us is because, unlike the previous problem, where as the box travels downward, the normal force always points the same direction, gravity always points the same direction, which means this entire time it's sliding, the acceleration was always 4.9 the whole way. Here, what's going to happen is as it slides down the ramp, the direction of the normal force is going to keep changing. Because for a curvy surface, the normal force is always perpendicular to a tangent line at that location. So like right here, at that little bump right there, here's a tangent line. So at that location, the normal force is going to point like so. But then like right here, the tangent line would be more like this. The normal force would point like so, different direction. When I'm looking here, the tangent line points very much diagonal. When I'm at the beginning, my normal force points basically straight up. So what's going to be really, really complicating for this shaped water slide is that because the normal force keeps changing direction, well, that means that my acceleration is going to keep changing, because now the normal force is going to cancel out a different amount of gravity. And at places where the normal force is basically straight up, it almost completely cancels out gravity. At those locations, the acceleration is going to be very close to zero. At other places where the normal force is almost sideways, what's going to happen is very little of that normal force is going to cancel out gravity, which means there's going to be a lot of acceleration. So when the thing is steep, there's going to be a big acceleration. When it's kind of flat, there'll be a small acceleration. And in order for me to do the kinematics part of this question, I'd have to be able to deal with an acceleration that keeps changing over the course of the slide. Now, the only way that I could do that using Newton's laws is with a hefty dose of calculus and with knowing very precisely the exact curvature of this slide, which, I mean, I can tell that it's bumpy, but I couldn't mathematically describe the actual rises and falls very easily without more information. So this is a nightmare if I try to solve it using Newton's laws. I can't do it. It's literally impossible. However, by the end of this chapter, we're going to be able to solve this problem. And not only will we be able to solve it, I'll be able to solve it in 2 lines, right? Now, to solve this problem using Newton's laws, I had a whole page worth of work. 2 lines. That's what we're going to use. So that's what our goal is. And the really cool part is that turns out, once we know this technique, I'm going to be able to solve this problem also in 2 lines. Spoiler alert, it's going to be the same answer. But in order for us to get there, we need to introduce some concepts. And the big concept that we introduce in chapter 7 is the concept of energy. Now, energy is one of those terms that if you've ever taken a science class ever, you've certainly heard the word, right? I know that even in a biology class, the term energy will show up, right? I remember back when Dr. Fail was here as our ecology professor, they used to do labs where they'd go out into the woods and they'd count the number of leaves to figure out the luminant intensity on those leaves, and from that figure out how much energy was available to that particular portion of the ecosystem based on how much light was incident on them, right? That's the kind of stuff that they would do. When a biological organism eats something, why are they eating things? Because they need the energy, right? So energy is a concept that you've certainly seen in biology and chemistry courses. But my suspicion is that many of you, if I asked you, what is energy, would have a hard time putting your finger on what it is. And that's because we tend to throw the term around, but we often don't have a very rigorous sort of definition of what that thing is. And here's the sucky part. It turns out if I gave you that rigorous definition, it's not especially satisfying, because the rigorous definition of energy, if you look in any textbook, they'll tell you it's the ability to do work. Okay. That doesn't mean much to us because, unfortunately, we've taken this one word that we've got that's kind of nebulous and difficult to wrap your head around it, and we've defined it in terms of this other term that we don't have a solid definition on. So in order to deal with that, we need to know what the heck work is. And in physics, work has a very specific definition, right? It's not like that place you go to because it's your job, right? That's not what work means. Work in physics means the exertion of a force through a distance. Right? That's what it means. You have to exert a force through some sort of distance. And that's going to be our definition of work. And in fact, what we'll end up doing is we'll mathematically express that as a product. So the work is going to be the product of whatever force you're pushing with times the distance that you travel. Oh, but it gets more complicated. Because it turns out that the force that you push with, it's a vector, right? Forces have both a magnitude and a direction. Now, when you think about distances, I could travel some distance to the right, I could travel some distance to the left. There's a direction associated with that as well. So what I'm doing is I'm multiplying two vectors together. And that's the first time in this class that we've done that. We've always multiplied vectors times non-vectors. Like there's equations where you'd have acceleration multiplied by time. Well, acceleration is a vector, but time is a scalar. And we've done plenty of stuff like that, but we've never multiplied two vectors together. So we're going to have to figure out how to do it. How do I take into account the direction part of that sort of multiplication? And what does that mean for my answer? And it turns out that there are two different ways to multiply vectors together. In one method of multiplying two vectors together, you'll multiply two vectors together and your answer will be a non-vector. Now, this is going to be one of those. Work is not a vector. Work doesn't have a direction. It only has a magnitude, a number part. And so in order for us to know that we're multiplying these two vectors together in a way that gives us a non-vector, we'll denote that by putting a dot in between them. We will call this the scalar product or the dot product. And it's a thing that we do in math. If I wanted to multiply two vectors together and have it be another vector, we would do that by having F cross D. So seeing the X in between says, oh, when I multiply these things together, that will be some other vector. So we'll do this in a later chapter. Right now, we're not worried about it. For now, we're dotting these vectors together. We're multiplying one times the other, but our answer is not going to be a vector. And how do I deal with the direction is what we're going to have to wrap our heads around. Now, here's how we'll do it, right? When we multiply two vectors together in this way, what we will end up doing is we will take the magnitude part of the force. That's just the number part, which by definition is positive, times just the magnitude of D, again, just the number part, by definition positive. But we'll deal with the direction portion by multiplying by the cosine of the angle between F and D. So when you see F dot D, know that in your head, you'll take the magnitude of F times the magnitude of D times the cosine of the angle between them, and that's how you'll calculate that dot product. Now, what does that mean in practical terms? Let's do a couple of examples. So imagine I've got an object, and I'm pushing that object with a force of, say, 50 newtons. And while I'm pushing it with a force of 50 newtons, it travels to the right a distance of 2 meters. So how much work did I do with that force? Well, if work is FD cosine of theta, well, the magnitude of F is easy, it's 50. The magnitude of D is easy, it's 2. And for the cosine of theta, it's the angle between these two vectors. But they're both pointing the same direction, so the angle between them is 0 degrees. Well, the cosine of 0 is 1. So it's just 50 times 2. It's 100. Let's think about units for a second. This is newtons times meters. We're going to give that a special name. A Newton meter is called a joule. So that is our SI unit of energy. So we did 100 joules worth of work in that example. Now, what if I change it up a little bit? What if instead I've got a force pushing straight up 50 newtons still. However, even though the object's being pushed upward, it's maybe traveling a distance of 2 meters to the right. Now, how might that happen? Well, imagine I've got this pen and there's a force from the table pushing upward. That's like the normal force. So as I slide it across the paper, the force from the table is pushing upward, but the object's moving sideways. So that might be the example. Now, how much work got done just then? Well, work is still FD cosine theta. And what's going to happen is F is still 50, D is still 2. However, the angle between F and D would be 90 degrees, and the cosine of 90 is exactly 0. So you can see that sometimes when I'm multiplying a force times a distance, if they're in the same direction, the work is literally like just straight multiplication, right? You know, I had a 50 newtons, 2 meters, so 50 times 2 is 100, and I got 100 as my answer. So when F and D are in the same direction, it's just like regular multiplication. But when they're perpendicular to each other, doesn't matter how big F is or how big D is, because they're perpendicular, I got no work at all. Weird. Let's change it up a little bit. What if I have my object pulling 50 newtons this direction, but the object is moving 2 meters in the opposite direction? How would that happen? Well, case in point for this, back in the day, I used to have a dog. She was a Saint Bernard, and this dog loved going for walks, but the word walk is probably not best applied because that's not what she did, right? What she would do is she would run through the entire neighborhood, and the entire time I'm just sort of hanging on her leash for dear life, trying to slow her down enough that I could keep up with her. That was the whole thing. So maybe that's what this is. This is me pulling on my dog's leash while she travels in the other direction the entire time. How much work was I doing when I pulled on that leash? Well, again, we'll do F D cosine of theta. And here, F is still 50, D is still 2, but now the angle between F and D is 180 degrees. And the cosine of 180 is -1. So you can see that what was happening is as she dragged me through the neighborhood, I was doing negative work on the dog. Kind of cool. And of course, you could have things in between. Right? If I have a force like so of 50 joules and a distance of, let's say, 2 meters, maybe this angle right here is 30 degrees. Well, now the work being done will be 50 times 2 times the angle between them is 30. And that's 50 times 2 is 100. But the cosine of 30 is not 1 or 0, right? Cosine of 30 is the square root of 3 over 2, which is about 0.866. So you can see that there was positive work being done, but it was less than the full 100 that we had when they were in the same direction. And that's kind of what's going to happen. And this also gives me a way of interpreting why we're using this cosine of theta to begin with, because let's think about what this is really doing, right? If I'm looking at this, what I've got is I'm multiplying D times F cosine 30. But what is F cosine 30? Well, if this is F, and I break F into X and Y parts, the X part is F cosine of 30, The y part is f sine of 30. So one way to think about it is that when you're doing these dot products, what you're really doing is you're multiplying the distance, 2 meters, by just the portion of the force, but just the horizontal portion of the force, and ignores the perpendicular part. So conceptually, that's what's happening, is when you do a dot product, we're multiplying the part of the force that's the same direction as D together, and we're ignoring any part of the force that's perpendicular to D. And that's why when we had this example, when all of the force was perpendicular to D, we literally got 0. When all of the force was parallel to D, it was literally like straight up regular multiplication. When it was exactly the opposite direction, we got straight up multiplication, but negative. And when they were partially in the same direction, we got a partial amount. We got less total work done when they were partially in the same direction. And so that's kind of the concept of work and how that's going to play out. So once we've done that, once we've broken that into portions, how can we make this concept of work in our favor? Well, the way this is going to boil down is there's going to be a relationship between how much work an object has done to it and how much velocity that object has. Those two things are going to be related, and we're going to exploit that to solve problems. Now, to think this through, let's start with something that we already know to be true. So back in chapter 2, we learned this equation. Excuse me. Now, we know that equation, and we also know that if I take any equation ever and I multiply both sides of an equation by the same thing, then the equation I get as a result is still true, right? We've done that kind of trick a gazillion times before. So we're going to do that here. Now, the thing that I'm going to choose to multiply both sides of that equation by, I'm kind of pulling this out of my behind a little bit, but it's because I know where I'm going. I'm going to choose to multiply both sides of this equation by the mass of whatever object we're talking about. So let's multiply both sides by m. So I'm going to have this times m. I got to have this times m. I got to take this. So plus 2 times m times a times yada, yada, yada. I just multiplied everything by m, right? It's the same equation. If I wanted to, I could cancel all those m's out and go back to where I started. But this equation, as I've written it here, should still technically be true, because I just multiplied both sides of the equation by the same amount. Now, I notice this term and this term, they look kind of similar. Let's get those on the same side of the equal sign. I'm going to subtract this from both sides. So I'm going to have mv final squared minus m the initial squared equals all this stuff. And heck, let's get rid of this 2. Let's divide everything by 2. So that means I don't have to divide this by 2. It'll be 1/2. I have to divide this by 2. That'll be 1/2. And then over here, this 2 just cancels out, and it leaves me m times a times yada, yada, yada. Now, what I see here is that on the left-hand side, I've got this weird expression, this 1/2 mv squared expression. But obviously, that's related to my velocity, right? This is the velocity I ended up with. That's the velocity that I started with. So somehow, all this garbage over here is related to how much my velocity changed by. Okay. But then I want to stop and think about what all this garbage over here means. Because wait a second. What the heck is MA? Oh, Newton's second law. MA is the sum of all the forces, right? F equals MA. So this is not just one force, this is the net force. It's the total of all the forces acting on the object that's moving around. Cool. Wait, what the heck is all this? Final position minus initial position. That's how far the object has gone. That's the distance that I've traveled. So on the right-hand side of this equation, I have my net force multiplied by how far I've just moved. Oh, wait, that is the work. More specifically, it's not just any work. Since this was the sum of all the forces, this is the sum of all the work. This is the net work being done by all the forces acting on my object. That's what that is. And look what that equals. Well, over here, I have this 1/2 mv squared and 1/2 mv initial squared. We're going to give this concept a name. We're going to call this kinetic energy. Right. So when you see 1/2 mv squared in your head, I want you to think kinetic energy. That's what it is. Now, apparently, this kinetic energy is related to how much work you had to do to make an object move at that speed. So the faster something is moving, the more kinetic energy it's going to have. And apparently, the more work you have done to you, the more your kinetic energy will change by. And in fact, this is my final kinetic energy. That's my initial kinetic energy. So I can write that as K final minus K initial, or more succinctly as delta K. And this is awesome. This is called the work energy theorem. Now, what's the big idea? How can I boil this equation down to like an idea that I can sort of vocalize? It says that if you've got an object and there's a bunch of forces acting on that object, if you tally up all the work done on that object by all those forces, it will tell you how much its kinetic energy has increased or decreased by, right? If the kinetic energy has, or if the work is positive, then the delta K is going to be positive. That means the object will have sped up. So when you do positive work on an object, it speeds up. When you do negative work on an object, it slows down. And if you do zero work on an object, then it's going to keep whatever velocity it had. It's, or I should say, it'll keep whatever speed it had, not velocity. I got to use my words carefully there. So that's cool. We have a relationship between how much work got done and how much kinetic energy I increased by. Awesome. So let's see if we can't put this to work a little bit. Let's go back and do another version of that ramp problem that we started with. However, this time what's going to happen is we're going to include an additional force to make it a bit more interesting. So this time, here's my box, here's my ramp. And what's going to happen is I've got the normal force, yada, yada, yada. I've got gravity, yada, yada, yada. Let's add some friction to my ramp, right? Let's have a frictional force this way. And what's going to happen is, let's see here. Let's choose a frictional force, and let's have a flat out frictional force of just flat out 10 newtons. I got a 10 Newton frictional force. And what I want to do is figure out what the speed of the box is when it gets to the bottom. Let's assume that the mass of the object is, how about 2 kilograms? And let's make it 20 kilograms, just in case. So I want to figure out the velocity of this thing at the bottom, and I want to use work and this work energy theorem to do it. Now, in order for me to make use of that, I'm going to have to figure out how much work got done. Let's assume that it's still starting at 10 meters high like it was before. I want to figure out how much work got done by each of the forces acting on this object. And I love this example because people who know the definition of work, if they know this, but they don't really understand it, they'll still get it wrong. So it can help me discriminate between students who kind of sort of know the formula and people who know how the formula should actually work. So let's start off with the force of friction, right? So I want to find the work done by friction. So it's going to be the force times the distance times the cosine of theta. And the force of friction was given in the problem. I told you flat out it was 10 newtons. So I know that F is 10. Now the distance it's going to travel is from here to here. We figured that out back when we did the previous problem. We know that this distance right here works out to be 20. So 10 times 20. Now, a student who doesn't know what they're doing, when they go to plug in the cosine of theta, their knee-jerk response is going to say, oh, look, theta is 30, and they're going to plug 30 in here. And when they do, they're going to get this question wrong because that's not the angle I want. And in fact, we're going to do three forces here. Not once is that angle going to be 30. Not one time will 30 degrees show up in this problem. Now, what's the angle between the force and the distance? Well, let's look at my picture. My force of friction is up the ramp, but my distance is down the ramp. So what's the angle between F and D? That's 180 degrees. So the actual theta that I'll use here is 180. Now, how much work did friction do as it slid down the ramp? Well, 10 times 20 is 200. Cosine of 180 is -1. It did -200 joules worth of work. Cool. Now, what about the work done by the normal force? Let's do the normal force. So what's going to happen is, in order for me to do the F part, I have to know how big the normal force is. And I've done enough of these ramp problems that I could figure it out if I wanted to. The normal force would equal mg times the cosine of 30. So hopefully you guys have seen this enough, you know this. If not, go back and review one of the previous classes. I don't want to do this in more detail. That's going to be my normal force. So there's my F. And again, what's that going to be? I could calculate it if I wanted to. It'd be 20 times 9.8. That's going to be 196 times the cosine of 30, which is the square root of 3 over 2. I don't know what that is. 169.7, something like that. I'm not super concerned because it's not going to matter. My distance, I'm still going 20 meters. But now when I do the cosine of theta, what's the angle between the force and the distance? Well, the normal force points perpendicular to the ramp. The distance is along the ramp. So the angle there is 90. Yeah, Jasmine, what's your question?
So I know you said that we don't want to do the 30, right?
Yep.
So with the 180, is that just going along the bottom of the ramp?
Well,
I'm sorry, I didn't catch what you were saying with
So
that.
the trick here is that the theta in this work formula is the angle between the force and the distance. So in order to know what that angle is, I looked at my picture and I said, oh, look, the force was this F. I'm going to draw it diagonally up and to the left. Right, there's my F. And the distance was going down the ramp. So the angle between that and that is 180.
Okay, got you.
Yeah.
I understand now.
So that's the trick. And so the 30 didn't come into play for that at all, right? For this one here, my normal force was like this way, but my distance was still down the ramp. So the angle for this one was 90 degrees. Right. Now we got one more to do. And we got the normal force. Well, wait a second. What's the number for that? Well, it doesn't matter what all this is because the cosine of 90 is 0, right? That whole thing is 0 joules. And you will find that that will almost always be the case because the normal force from a surface is always perpendicular to that surface. So if you're sliding along that surface, your motion is always perpendicular to the normal force. So the normal force almost never will do work. The only way I could make the normal force from like the floor do work is if I did something like I got in an elevator, right? In an elevator, the normal force pushes you up and the elevator moves up. So there, the entire floor had to move with me in order for the normal force from the floor to do any work at all. If I've got a stationary table or a ramp or whatever, and that ramp is not moving, then it's not going to do any work at all. And that will often be the case. Now, one last force to do, and that's the force of gravity. Now, again, I'm going to do F equals F times D times the cosine of theta. And the force of gravity is easy, right? It's M times G. So what is M? M is 20, G is 9.8. So 20 times 9.8 is 196. D is still 20. But now I got to do the cosine of the angle between F and D. And this one's a little bit tricky. So gravity pointed straight down. There we go. The distance is straight along the ramp. And what I know is like, if I was doing like the components of mg, there's the y component that runs perpendicular to the ramp. I know this angle right here is 30. But that means that this angle is 30 and this are perpendicular. This angle right here, which is the theta that I want, has to be 60. So I would do cosine of 60. So again, wasn't 30 degrees. 30 degrees didn't matter. And so now, what's the cosine of 60? It's a half. So that's going to, I don't know if I can get my calculator out. That's stupid. I do it in my head. That's going to be 1,960 joules. So how much total work got done by this on this box by all these forces? Well, the total work is going to be 1960 plus 0 plus negative 200. So the work net is going to be 1760 joules. And what can I do with that? Well, now I get to go back and I can use the work energy theorem because I know this and I can find the change in kinetic energy. So if the net work is the change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared, and I'm starting from rest, so this is equal to 0, and I want to find what speed I have at the bottom, all I've got to do is solve that for v. So 2 times the net work divided by the mass equals v square root. So all I had to do is just rearrange this to solve for v, and I'm good to go. So 2 times 1,960 divided by 20, and then I square root that bad boy. And so 1960 times 2 divided by 20, square root. I get 14. Oh, that's because it wasn't 1960, stupid. It was 17. I was like, why is that so much faster? It's 1760, not 1960. I was very confused for a moment. So 13.26. Super easy.
So is the one for the gravity 1760 or that's still 1960?
Well, the 1960 was the work done by gravity, but we had to
Okay.
add the work done by friction, which was negative 200. I forgot to subtract the 200.
Okay, okay.
Yeah. So that was where we got that from. All right, so now here's where I realized I was stupid earlier, and nobody called me on it. Because notice I did this by mistake just now, where I put in the work just from gravity, and I did the 2 times the 1960, where I didn't include the work from friction, and I got exactly 14. Whereas when I included the friction, it went a little bit slower, which that makes sense, right? Friction should slow you down. So your speed, if there was no friction, should be faster than your speed if there was friction. But wait a second. We already solved the problem of what happens if you slide down the ramp and there's no friction, right? We did that problem already, except what did we get as our answer? Not 14. So how come I got a different answer here than I got here? That doesn't make any sense. Do you guys see it? We made a mistake earlier, or I should say I made a mistake and nobody said anything. If you look closely, you can see it. So right here, I have v squared equals 2 times 4.9 times 20, right? But then in the very next line, what did I write? 2 times 4.9 times not 20, but 10. So between this line and this line, that 20 got turned into a 10. It was supposed to be a 20. But now 2 times 4.9 is 9.8 times 20 is not 98, it's 196. The square root of 196 is not this, it's freaking 14, which is the same answer we got over here. So if I had made a stupid math error, we would have got the same answer doing it the long, complicated way with Newton's laws as we got doing it the super easy way with just looking at the work. And that's kind of the whole point, is that it doesn't matter what method you use, you should get the same answer for the same problem. So, oops, that was embarrassing. Can't believe you guys didn't stop me on that. So that's all, I guess, fine and dandy. Yay, we can use this work energy theorem to figure out some kinds of problems. But it wasn't like it saved us all that much work, because we still had to do, for this problem, we still had to do the work from friction and the work from the normal force and the work from gravity. That was a whole lot of work, right? There was less vector stuff going on, but wasn't that much easier. So far, not that great. Plus, we still have the problem of, if I'm trying to do the water slide problem, where I've got this weird bumpy ramp, I still have a hard time calculating the work done by the weird bumpy ramp because of that weird shape. So we're going to need to make one more, I guess, revelation before this is useful to us in a really good way. And it has to do with the fact that there are certain forces that always do work in a super predictable way. And because they're always going to do work in a super predictable way, we'll be able to take some shortcuts, right? And to get a sense of what I mean by that, let's consider the following situation, all right? I want to imagine an object, and let's just say it's got a mass of 2 kilograms, okay? And what I'm going to do is I'm going to take that object and I'm going to take it on a little trip. It's going to start right here. I'm going to lift it up, let's say 2 meters. All right, then I'm going to go sideways, 3 meters. Then I'm going to drop it back down 2 meters. And then I'm going to go back 3 meters. So I'm going to take it on a little trip clockwise around that rectangular path. And what I want to do is to calculate the work done on this object by the force of gravity. So if I do that, remember, at each section, the work is going to be F times D times the cosine of theta. And the F is going to be the force of gravity, which is M times G. That's 2 times 9.8. That's 19.6 newtons of force every possible leg of that trip. However, what's going to happen is on this leg of the trip, I'm moving up. So the D points upward, but gravity points downward. So during this section of the trip, the cosine of theta is going to be the cosine of 180, which is -1. So the work done for the first part of the trip, I'll call that work 1, is going to be 19.6 times 2, right? It's going to be 39.2. Times the cosine of 180, but the cosine of 180 is -1. So it's going to do -39.2 joules, lifting it from here to here. Now, I'm going to go sideways some. How much work got done going sideways? Well, for that, the force is still going to be 19.6. The distance is 3. And I could multiply that out if I wanted to, but it's not going to matter because the angle between the distance over here and the force is 90 degrees. The cosine of 90 is 0. So there's 0 work done going sideways like this. Now, what about going back down again? Well, as I go back down, what's going to happen is the force is still 19.6. The distance is 2. So 2 times 19.6 is 39.2 still. But now the distance is downward. The force of gravity is downward. They're both the same direction. So the angle between them is 0, and the cosine of 0 is 1. So here, for the third section, the work is going to be positive 39.2. Now, when I go back sideways, the distance is to the left, gravity is straight down, the angle's 90, and for the force portion of the trip, the work done is 0. Now, if I tally up all the work done by the force of gravity over that entire closed path or round trip, hello, Max, thank you. Random drive-by, no smoking. The total work is just this plus this plus this plus this, which is 0. So for this entire trip, gravity did a grand total of 0 work because it did negative work part of the time and it did positive work another part of the time, and they exactly canceled each other out. Now, maybe that just has to do with the fact that I moved in a little rectangle. What if I didn't move in a rectangular shape? What if I picked a different kind of path? Let's mix it up a little bit. So imagine now that I take my same little object. I'm going to go 2 meters up, 3 meters over, and instead of coming down and back, I'm going to go straight back. How much work got done over this whole path? Well, 2 out of 3 of these legs, we already know, right? From here to here, the work, we already calculated it, was -39.2 joules, right? That's not going to be any different. From here to here, the work was 0. So how much work got done here, we'll have to figure out. Now, to do that, remember, it's going to be F times D times the cosine of theta. And F is M times G, which is still 19.6. Now, D is going to be whatever this diagonal distance is. Now, how big is that diagonal distance? Well, I notice this is a right triangle, right? And so I could find that hypotenuse using the Pythagorean theorem. It would equal the square root of 2 squared plus 3 squared. And I could calculate what that is. I'm just going to write it down like this, and you'll see why here in a minute. So 2 squared plus 3 squared, whatever that is, 4, 9. So square root of 13, so I don't know, 3 point something, times the cosine of theta. Now, what the heck is theta? Well, theta would be the angle between the distance, which is that, and the force, which is that. I don't know what that angle is. However, I could figure it out because I know that this angle here is the same as this angle here. That's one of those theorems. If I have two parallel lines and a transversal running across them, the alternating interior angles are congruent. You learn it in geometry. But here's the cool part. Look at this triangle right here and this angle right there. I'm looking for the cosine of theta, right? The cosine should be the opposite over the hypotenuse, or should be adjacent over the hypotenuse. So I don't even need to know what that angle is. I know that the cosine of that angle, whatever the heck it is, should be the adjacent side of the triangle, which is 2, divided by the hypotenuse, which is the square root of 2 squared plus 3 squared. So let's just replace the cosine of theta with this. And you can see now why I didn't bother to figure out a number for this, because look, this and this, they're going to cancel anyway. And 19.6 times 2 is, oh, wait, positive 39.2, which is the exact opposite of the other work. So the work done over that entire path was still 0. And here's the cool part. When it comes to gravity, it doesn't matter, right? Whatever path you take, whatever directions you go, if you start someplace and you come back to your starting point and you tally up how much work gravity did over that entire closed path, no matter how complicated that path is, the work will always end up being 0, period. And that's awesome, right? It means that, like, when I was doing this, and I knew that going from here to here, I was doing negative 39.2 joules worth of work. It meant that if I always got 0 when I come back to here, it doesn't matter whether I go down and over, or whether I go straight, or whether I take some weird, crazy, complicated, bumpy path. The work that got done by gravity going from here to here is the same going straight or down and over or over a weird curvy path. It'll always be 39.2 every single time. And so it means the work done going from point A to point B won't depend on what path I take. It doesn't matter. So for this kind of force, like gravity, the work is so predictable that a lot of times we can take a hard problem and not solve it, because we can instead solve some easy problem, but we know the answer is going to have to be the same. And that is the power of using work to solve these sorts of problems. We can take the complicated problems that are impossible, and we can be like, I'm not going to do that, because I know here's this easy problem that I can do super simply, and it's going to be the same answer. So I'll solve the easy problem and then just use the same answer. And that's what we're doing. So we call this kind of force any force for which it is true that the work done over any closed path will always equal 0. We call that a conservative force. So when I say a force is conservative, no, I don't mean that it watches Fox News and it ruins America. No, what I mean is that a conservative force is a kind of force for which the work done over any closed path what I mean by a closed path is a round trip. You start someplace and you come back to where you started, will always be 0. Right. An example, gravity. Gravity is a conservative force, right? It's kind of the canonical example of conservative forces. Now, there are some forces that are non-conservative. And non-conservative forces, they're going to end up doing some work that's non-zero over a closed path. Right? And this is why that's important. For a conservative force, because this has to be true, the work done can't depend on the path. In other words, if you're going from point A to point B, the work done is going to be the same no matter how you get from point A to point B. If you go in a straight line, you get a certain number. If you get on a plane and fly to Cleveland and then do a great circle route, circumnavigation of the world, then you come back to point B, it's still the same amount of work. Right? But for a non-conservative force, the work will depend on the path you take. If you take a different path, you might get a different amount of work. Now, an example of a non-conservative force would be something like friction. Friction is a non-conservative force. To see why, consider the following, right? Imagine that here's a table, and here's a box, and let's imagine that I scoot this box from one side of the table to the other, a distance of 3 meters. And the entire time, there's a frictional force that's opposing that motion. So it's moving to the right. There's a frictional force of, let's say, 10 newtons. Now, to go from here to here, the work would be 10 times 3 times the cosine of 180. So that's negative 30 joules. So to go from here to here, friction would do negative 30 joules worth of work. But if I go from here back to here, well, what's going to happen is on the way back, the force of friction is going to be the other direction. And the distance is going to be this direction. So the angle is still going to be 180, which means on the way back, it's going to do another negative 30 joules of work for a total of negative 60. So that's a non-conservative force. I went someplace and I came back to where I started. And because the direction of the friction reversed when I changed direction, it was doing negative work the entire time. And that's important because it means the path I take matters. If I had scooted it further out and then scooted it further in, going over that longer path would have meant more negative work. If I went, 4 meters out and 4 meters back, it would have taken me more work than to go 3 meters in and 3 meters out. The path mattered. And because of that, non-conservative forces are less helpful in energy conservation problems. They're going to make our lives a smidge more complicated because of that. So now that we've got this idea of conservative and non-conservative forces, what we're going to do is let's put it all together and use this to solve super easy problems. All right, let me pause this for one moment. Back to recording. All right, so let's go back and do that impossible problem. But this time we're going to use energy, or what we know about work and conservative forces, to make our lives easier. And here's the trick. What we're going to do is that for every conservative force, we're going to define something called potential energy. Right. And the potential energy is going to be the energy stored in the position of an object by a conservative force. every conservative force is going to have an associated potential energy expression. And the easiest one to do is probably gravity. Look, here's my pen. And what's going to happen is right now, my pen is sitting right here. If I lift my pen up some distance, gravity is going to do work on my pen. Now, because I'm lifting it up, the force of gravity is down, but it moved up. So the angle between the force and the distance was 180. So gravity did a certain amount of negative work when I lift my pen up. Now, that's negative work is like gravity taking energy away from my pen. Now, where did the energy go? Is it gone forever? No, because if I drop my pen and it falls back down to where it started, whatever negative work gravity did on the way up, on the way down, the force of gravity is downward, it's moving downward, the angle is 0. It's going to do that same amount of work on the way down, but positive. So the energy that gravity took away when I was lifting it, it wasn't gone forever. Gravity has stored it up and saved it so that when I drop it back down again, it can give that energy back, right? The way I kind of think about this is, if you think about potential energy is like your bank account, and the rest of your energy is like the money you have in your pocket, right? If I have $100 in my pocket and I go to the bank and deposit it, the money's not gone, right? It's not in my pocket anymore, but it's saved up in my account balance. And I could always then choose to withdraw it, make the bank balance go down, and the money in my pocket go back up again, right? So the money's still there, it's just not on me, right? In the case here, the energy is still somewhere, it's just stored up by gravity, and when I come back down again, I'm going to get it back. And so we're going to define the potential energy for any conservative force ever, in terms of the amount of work done by that force. Come on, dude. There we go. So we will say that the potential energy, and we're going to use the letter U for potential energy, is going to be related to the work done by that conservative force. However, here's what's tricky. When the force does negative work, like when I lift the object up and gravity does negative work on it, the amount of potential energy is increasing, right? Because as it does negative work, it's stashing it away. The bank balance is getting bigger. So it'll be the opposite of the work done. So if the work is negative, that means my potential energy got higher. And if my work was positive, my potential energy got lower. And for gravity, we'll be able to come up with an expression for that, because the work done by gravity is easy, right? Remember, work is FD cosine theta. And the F and the D, that's going to be mg, and this is however high I lift it. So the work done by gravity, if I lift something up, would be negative mgh. And so therefore U would be the negative of negative mgh, which is positive mgh. So this is called the gravitational potential energy. And that's super cool. We're going to be able to use this concept of the gravitational potential energy to keep track of how much work gravity is doing going from point A to point B. And that is going to allow us to solve problems super, super easily. Because check it out. Let's imagine that I have a situation where there's an object, and that object is under the influence of nothing but conservative forces. There's no non-conservative forces to be found. Now, what I know is the work energy theorem says that the net work is equal to the change in kinetic energy. That's the work energy theorem. And what's going to happen is, if I've only got if I only have conservative forces, the work is going to be related to the change in my potential energy. But because of that minus sign, I can replace this with negative delta U. And again, this is just like, if you think of the kinetic energy as the cash in your hand and U as being your bank balance, what this is saying is that when you take money out of the bank, the amount of cash goes up, but your bank balance goes down. That's what that's saying. And now if I just rearrange that, well, remember, delta means final minus initial. So this is final kinetic energy minus initial kinetic energy. And over here I have negative, this is final potential energy minus starting potential energy. If I distribute that minus sign through, that's just going to flip those signs. So I have U initial minus U final. And then if I rearrange this one more little bit, if I get all the initial stuff on one side of the equation and all the final stuff on the other side of the equation, I'll have U initial plus K initial equals U final plus K final. And this is the most powerful statement in all of chapter 7. Because think about what that means. This says if you take any object and you add up how much kinetic energy it has and how much potential energy it has, this together is like what we call the total mechanical energy. It says whatever total amount of energy you start with has to be the same as the amount of total energy you finish with. So whatever energy you start with, you'll have the same at the end, no matter what. That's awesome. And again, going back to my money analogy, it's like saying the total amount of money you have both, in your pocket and in your bank account, as long as you're only depositing or withdrawing checks and you're not, buying things and giving money to other people, you have a closed system, the total amount of money you have will stay the same, right? I can't lose money by making a deposit in the bank because my bank balance might get bigger, but my cash on hand is going to get smaller by the same amount. My money doesn't disappear. That's what this is saying. This is the statement that says the energy is conserved. It's neither created nor destroyed. Whatever energy you started with, it might change forms. It might turn from potential energy into kinetic energy, but it doesn't just vanish. And if I've got nothing but conservative forces, this is true. Now, how on earth am I going to use this statement to solve that impossible problem in 2 lines or less? Well, here's that impossible problem, yada, 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 yada. This thing had a height of 10 meters. The box is up here. And I want to know the speed down here at the bottom. So what are the forces acting on that box? There's gravity. But gravity, I know for sure, is a conservative force. There's also a normal force from the ramp onto the box. But what I know is that at any given moment, the normal force is going to be perpendicular to whatever direction the box is moving, which means the normal force can't ever do any work. And if you do 0 work on the way out, you'll do 0 work on the way back. The normal force is almost always going to be a conservative force. There's no friction, which would be non-conservative, which allows me to say that all the forces in this problem are conservative forces, which means I can say the following statement has to be true. Now, what's the definition of K? Remember, kinetic energy is 1/2 mv squared. Potential energy for gravity is mgh. And all I've got to do is use these to fill in these blanks and then solve for stuff. Now, my box started out here stationary. So its original velocity was 0. So K initial is 1/2 m times 0 squared. That's freaking 0. Now, U initial is mg times the height. How high is it? 10 meters. So right now, this is going to be m times g times h initial, and that we know to be 10. Now, when it gets all the way down to the bottom, how it gets there is not going to matter. How much kinetic energy does it have? I don't know, but it's probably going to be traveling pretty doggone fast. So it's going to have some 1/2 m times v final squared, and we're going to solve for v final. What about u final? Well, that would be m times g times h, but when it's down here, it's at a height of 0. That's conveniently 0. So all I've got to do is solve that equation for v. And notice, I never told you what the mass of the box was, but it turns out, since it shows up on both sides, it'll cancel out anyway. It won't even matter. So now when I solve for V, I'm going to multiply both sides by 2. So I have 2 times G times H initial equals V squared. And therefore, the square root of 2 times G times H initial equals V. So that's 2 times 9.8 times 10. That's 196. Square root of 196 is 14 meters per second. Boom. Here's a problem that we said at the beginning of class was going to be impossible. And dude, it was like super easy. And super cool thing, we got the same answer here that we got on that previous problem. The shape of the ramp didn't even matter. That's super awesome. So that's the big picture from chapter 7, right? We're going to take impossible problems, reduce them down to energy conservation problems, and we'll solve them in no time flat. Now, energy conservation can't do everything for you. I know that when I first learned this and we got to this point in the process, one of my classmates said, Dr. Mays, I don't understand why we're doing all these hard problems from before if we could do these same problems this easily. And the answer is we had to do the methods the old ways because there's some things we can't answer with energy conservation. For instance, if I want to know how fast I'm going at the bottom of this hill, we did it. That's easy. But what I don't know is how long it takes me to get to the bottom of the hill. If I wanted to know, say, the time it took, that's gonna matter. And I'd have to do that using Newton's laws. What's more, if I were to say, have a box on a straight ramp of 10 meters high, a box on a slanty ramp, 10 meters high, a box on a curvy ramp. If all these ramps were frictionless and 10 meters, well, energy conservation would look exactly the same for all three of these problems. When you get to the bottom of each of these, all three of these boxes would be traveling the same speed of 14 meters per second. However, they would not arrive at the same time. Because what's going to happen is this box right here starts off super steep. So it's going to start off with a super big acceleration, and it's going to pick up speed really quickly. So it's going to spend a lot more time going fast, and that means it's going to cover the ground pretty quickly. This guy here is probably going to arrive before either of the other two. Meanwhile, this guy here is going to start off with a nearly flat slide. It's going to have a very tiny acceleration, so it's going to take a long time to build up to 14 meters per second. So this guy here is probably going to arrive at the finish line last. This guy here will be somewhere in between. He would have one acceleration of 4.9 it was the entire way, and it would take a certain amount of time for him to get there. But this guy would get there quicker, this guy would get there slower. And to know the times, I'd have to do Newton's laws and kinematics and all the stuff we've already learned. Those are all tricks that energy conservation can't tell us. But what I do know is that regardless of the amount of time, it may take this guy half an hour to get to the end of the ramp, but when he does get there, he'll have a speed of 14. This guy might get there in a second, but when he gets there, his speed will only be 14, right? So that's the process that we'll be utilizing to solve every problem in chapter 7. And they're all going to end up being super easy. That's sort of the overall point. And in fact, if you were to be so misfortunate as to take like advanced versions of this class, what you would find is that we stop talking about forces in advanced mechanics classes pretty quickly. And almost everything is done in terms of energy, because energy will allow us to figure out a whole lot of stuff that used to be impossible and now is almost trivially easy. All right, that was it for for that part of chapter 7 at least. Are there any questions? You guys feel like this makes sense?
Yes, for the most part.
Okay, good deal. So for my money, what's going to happen is chapter 7 and 8, the conservation law chapters, are some of the easiest chapters in this book, right? So if you've been a little struggling because the previous couple chapters have been kind of tough, it's going to get easier for a bit. So yay! And the whole concept boils down to remembering that energy is conserved. So the energy that I have originally has to be the same as the energy I have at the end. And by setting that such situation equal to each other, you can solve for whatever information is missing. All right, so if you haven't done so already, remember the exam is due tonight at midnight. So make sure you take a crack at that and don't wait till the last minute, because especially if there are technical issues, if I don't have time to fix them, you're kind of out of luck. So good luck. I'll see you guys later.
Thank you.
You're welcome, folks.